over gamma of, what is it?
Alpha prime u plus
Alpha prime u plus 1.
plus 2.
Plus 2. Minus alpha prime u plus alpha prime u plus 2.
Yeah.
2. Equivalently, this stuff here, using s plus t plus u is equal to 1, was, and that's the way we actually obtained it, was gamma of minus alpha prime s minus alpha prime u, t minus 2. Okay, when we had this plus the other permutation, gamma of minus alpha prime s minus 1, gamma of minus alpha prime u minus 1, divided by gamma of plus alpha prime t plus 2 plus gamma of minus alpha prime minus 1 gamma of alpha prime u minus 1 gamma of alpha prime t plus 2, and we had
Yes.
excellent, thank you, and we had alpha prime into s plus t plus u, alpha prime into s plus t plus u was equal to, now was that minus 1? Let's see, s was p squared minus s squared. Right? So it's a positive quantity if we were dealing with, so this is minus 4. Is this right? Okay, excellent. Because the minus was the fact that we were dealing with tachyons. Right? It's 4n squared. Excellent. Okay, so let's just start. Okay, so in the last class we discussed, and I'll quickly remind you, that we had this stuff times what? Times a factor of 2, because you remember there were 6 cyclic ordinates which were pairwise equal. Was this you remember? Okay. Times you had a factor of g tachyon to the 4. Where g tachyon was just the normalization factor behind e to the power k dot x in the scattering amplitude. That was just because of 4. That's 6. And times you had the factor of the determinant of the matter plus world sheets fields on the disk times e to the power, the integral over the dilaton. That whole object we're going to call C disk. Okay? So we got this stuff in a 2 times g tachyon to the 4 times C disk. Okay. Let me remind you what we got when we did 3 tachyon scattering. When we did 3 tachyon scattering, we got g tachyon q. Just because 3 tachyons, we got the same factor C disk. Because C disk is just the determinants in the absence of an insertion. It doesn't matter how many insertions you have to consider with the disk. And we got a factor of 2. Can somebody remind me why we got the factor of 2?
Which unpacking factors there are 2 possible?
There's 2 possible cyclic absorptions. 1, 2, 3, or 1, 2, 3. Okay? Had we put in the Chern-Paxton factors, this factor of 2 would become a factor of the 2 waves, the 2 terms in the trace. Okay. At the moment we're ignoring the Chern-Paxton factors, I'll put them in just a minute. Okay. So now we did this last time, but I'll do it again, being a little more careful with the numbers. We wanted to factorize this guy on poles. Okay? We wanted to factorize this guy on poles, and from that factorization, and unitarily see what we can say about this C. Okay? So factorizing this guy. So let's say that we factorize this on the pole, the tachyon. Let's remember where the tachyon pole was. The tachyon pole was at S, alpha prime S is equal to minus 1. Okay? Let's remember firstly where this guy had poles. This guy had poles whenever minus alpha prime s minus 1 was a negative integer. It was 0 or a negative integer. It was equal to 0, minus 1, minus 2. Now it's the same equation as alpha prime s plus 1 is equal to 0, 1, 2, blah, blah, blah. Okay? So alpha prime s is equal to minus 1, 0, 1. Okay? So we had poles in the S matrix, in this term in the S matrix, in S, when this equation was satisfied. The pole at minus 1 was the tachyon pole. The pole at 0 was potentially the what pole? Photon, the gate photon, exactly. The pole at 1 of first excited string states, the first massive string states, and so on. Okay? And in the last class, we computed the residue of this pole. I'll just do that again. So we want to set alpha prime s is equal to minus 1. But from the fact that alpha prime s is equal to minus 1 and from alpha prime s plus t plus u is equal to minus 4, if we substitute this guy as minus 1, we can conclude that alpha prime t plus u is equal to minus 3. Okay? Now because of that, alpha prime u plus 2, okay? So alpha prime u plus 2 is equal to minus alpha prime t minus 1. And therefore these two terms become just 1. I mean the ratio is just 1. Okay? You remember that the residue of the pole gamma at or gamma of x as x goes to 0 is simply 1 over x, the leading order. So this part just gives us 1 over this quantity, and these two guys cancel. So we get a pole from that guy of strength 1. Okay? Here we don't get a pole because we didn't have a gamma in the numerator. But here once again we get a pole. Once again of strength. Okay? So our net pole has strength 2. The two terms are identical, they're just numbers. We have an explanation, by the way, for the fact that the coefficient of the pole was independent of t or independent of u. Can somebody remind me of the explanation? It was an explanation of mutativity. The explanation was simply the following. You see, the coefficient of the pole has to be 3 tachyon scattering squared. So suppose we've got K1, suppose you've got a Feynman diagram which is K1, K2, going to K1 plus K2, so K, K3, K4. But K is of course the momentum conservation. Then the residue of this pole is simply this K1 to K2 goes to K, that's scattering amplitude, times K3, K4 goes to K, that's scattering amplitude. Just by unitarity. Okay? But if you've got 3 scalars and they're on shell, then the 3 particle scattering amplitude cannot depend on the momentum. Just from Lorentz invariance. You see, the 3 particle scattering amplitude is some function of K1, K2 and K3. But because these guys are scalars, so there are no polarization tensors to calculate. All indices have to be absorbed in dot products. So I think it can depend on K1 squared, but that's m squared. Or it could depend on K2 squared, K3 is the same thing. It could depend on K1 dot K2. But K1 dot K2 is the same thing as K1 plus K2 the whole thing squared. Minus K1 squared minus K2 squared by 2. Each of these is mass shell. It's determined to be a mass. Okay? So there's no data on which 3 tachyon scattering amplitudes can depend on general grounds of Lorentz invariance. We found this, by the way, also from explicit calculation of 3 tachyon scattering amplitude. We found that was a constant. But that we knew on general grounds from Lorentz invariance. Okay? So any pole that comes with any 4 scalar pole, in the pole of 4 scalar scattering, where the pole comes because of scalar exchange, you see, the coefficient of the pole, the residue of the pole, has to be just a number. if unitarity is being obeyed. Because it has to be the 3-point function squared, and the 3-point function was a number, it couldn't depend on it. It couldn't depend on K1, K2, K3, K4. In particular, in this way of writing, you think of the amplitude as a function of S and T. You've got a pole in S, but in general you might think that the residue is a function of T. If you're doing 4 scalar scattering, and the pole is also that of the scalar, the residue has to be independent. Okay? And that's what we see. So we're just comparing numbers, so that's our numbers. Okay? Now, let's compare these numbers more seriously. You see, in order for unitarity to work, what we need is that 2 copies of this amplitude, this guy and this guy, is identified with the residue of this pole. Okay? So we take 2 GT cube CT, square it, and identify it with 4 GT to the 4th speed. Why did I get the factor of 4? Well, because the amplitude had an overall 2 outside here. Because there were 6 cyclic orderings. And we had 2 places to get the pole from. Then we here and here. Okay? So that added up to plus the 4. Okay? So this equation now can be solved for as an equation that determines this determinant. Okay? This determinant is the kind of thing we try never to evaluate in quantum field theory. Right? We try to only evaluate ratios in which the overall partition function, 0 temperature partition function, cancels out. Here actually becomes physical. Because remember, the string scattering amplitude is not correlation function divided by partition function. Indeed, correlation function divided by partition function will be ill-defined. Because the string bosonic string path integral with no C insertions is 0. So we needed the insertions to get something non-zero to start with. Okay? So the idea of dividing by the path integral with no C insertions makes no sense in getting fit. And that's not what string theory instructs you to do. You want full path integral with the insertions, including. Okay. And okay, now that's a bit uncomfortable because it's the kind of thing we try not to calculate with quantum field theory. Okay? So this is one way. So there's this determinant factor which you may not know what to do with. One way of determining it is by demanding space-time unitarity. Now space-time unitarity here works. You see, the fact that it works up to a number is the non-triviality. Okay? For instance, you have some scattering amplitude. It needn't have been that even that you have the poles in the right places, even if you have the poles in the right places, it needn't have been that the residue of the pole was the right function of t to allow for unitarity to work. That works. So it works provided CD squared is equal to 1 over GT. And in CD squared, I'm including both the cos determinant, the matter determinant, as well as the dilaton factor. Okay, the square root GR factor. Okay? Now, you may be a bit uncomfortable about this. You may be a bit uncomfortable about unitarity. I'll tell you later about how ratios of determinants have been carefully evaluated using particular regulator schemes and give exactly the right answers that you get from unitarity. But at the moment, we're just going to use unitarity as a guiding principle. And I'm emphasizing this is not, it does not remove the wonder of what's happening. Because all we use it for is to fix one number. But the rest of the structure has to work by itself. Okay? Right. Any questions?
CD is equal to 1
CD is equal to. Thank you.
The formula is applicable even for these particles in space, right?
Which formula?
The scattering.
The scattering.
But then the argument for the 3-point function does not apply.
The argument for the 3-point function does not apply, and the result that the residue is independent of T also does not apply. Okay? So let's work one of those out. let's now work out the residue of the pole at S equals 0. This is an interesting pole. There's two tachyon to gate boson. Now, let me first work it out without Chan-Patten factors, even though you already know the answer should be without Chan-Patten factors. What should the answer be without Chan-Patten factors? What's the 3-point coupling? In what representation of the gauge group is the tachyon? Adjoint representation. Excellent. So, working without Chan-Patten factors is the same as doing U1. Chan-Patten factors makes it UN theory, but no Chan-Patten factors is U1. What is the adjoint representation of U1? U1 is all representations of U1 are labeled by a charge. What charge should I associate with the adjoint representation of U1? How does something in the adjoint representation transform under a unitary transformation? UA U inverse, exactly. Now when everything is just a number, what is UA U inverse? It's A, which means under U1, the adjoint representation is the uncharged representation in U1. So in U1, the tachyon is not charged, and therefore the tachyon-tachyon gate boson coupling is 0. You could have got this answer by applying the rule that when you ask a question in class, the answer is usually 0. Okay. We actually checked this. If you remember, you gave us the argument for why it was 0. Do you remember the word? Do you remember we computed the 3 vertex operators, tachyon, gauge boson, and we found a non-zero looking answer except those 2 terms and they cancelled each other because the C determinant picked up a -1. Okay, we actually checked this, that without the Chan-Patten factors we got 0, but with the Chan-Patten factors we got something proportional to the commutator of the Chan-Patten. So of course what we should expect to get here is 0. Okay? But anyway we're going to work it out. Just because the 0 happens a bit non-trivial. It happens by 2 terms cancelling each other. And once we've worked it out, putting in the Chan-Patten factors is very easy. Okay? So let me work out the pole from gauge boson exchange, the photon exchange. Just in the U1 theory first, and then we will complicate life with Chan-Patten factors. Okay, so I'm rubbing out everything except the Venetian amplitude. Okay. Now so what we're interested in is evaluating pole at S is equal to 0. So we just set S equals 0. From this formula that tells us that alpha prime of T plus Q is equal to -4. Okay. So near S is equal to 0, the argument of this gamma function is near -1. Okay? And the first thing that we want to do is to understand what gamma of x is when x is near -1. So that's an easy thing, because gamma of x is equal to x minus 1 times gamma of x minus 1. But if x is near -1, x minus 1 is near 0. And gamma of x minus 1 when x minus 1 is near 0, and I get wrong because this x. Let me run that. What's the formula? Gamma of n plus 1 is equal to n factorial, right? So, gamma of n, which was secretly n factorial, n minus 1 factorial. So, gamma of n is equal to what into gamma of n minus 1?
N minus 1.
It's n minus 1 into gamma of n minus 1.
Because gamma of n minus 2 will be n minus 1 is n minus 2.
Correct. Right, so this is right. So if x is near minus 1, this is the wrong formula to use, because this will set this near minus 2. Sorry, I should have used the other way. Let me start this again. Suppose we know that gamma, let's start with x near 0. That's what you're saying. Yeah, thank you. X is near 0. So that is equal to x minus 1 gamma of x minus 1. So this is what we want to find. We want to find gamma of an object near minus 1. So we have the formula that gamma of x minus 1 is equal to gamma of x by x minus 1. This is always true. And then
We knew that gamma of x.
then we put in the fact that x is near 0. So that is near minus 1. So this is equal to minus gamma of x. But we know gamma of x is 1 by x. Okay? So 1 by x. Okay? So up to a sign, once again what we see, and signs we will not try to be very careful about it. We could go through next round of care keeping track of signs. Actually, signs are important because unitarity requires squares of units. And a square is always positive. So signs are important. But at this round I won't try to keep track. Okay, so but after a sign, this pole also has this strength. So the rescue comes entirely from this ratio. Okay? Now, let's look at the ratio. So, the ratio is gamma of minus alpha prime t minus 1 divided by gamma of alpha prime u plus 2. Now the substitute where u is in terms of t. So alpha prime u, so alpha prime u plus 2, so alpha prime u plus 2 is equal to minus 2 minus t, minus alpha prime u. Okay, so this is equal to gamma of minus alpha prime t minus 1 over gamma of minus alpha prime t minus 2. Okay, so that's not too bad because the numerator is gamma of minus alpha prime t minus 2 into minus alpha prime t minus, using the fact that gamma of x is equal to x minus 1 times gamma of x minus 1. And then this cancels this. So the ratio is minus alpha prime t minus 2. Okay? So we see that from here, and I said I won't keep track of signs, but I better keep track of signs because the signs are going to, I'm going to get cancellation because of signs. Yeah, so from, this camera business is very frantic. Anyway, so what we have is minus 1 minus of minus 1 times minus alpha prime s is 1 by 1 over the argument, whole, times minus alpha prime t minus 2. This was our, I mean, this was the singularity, and this was the residue of that singularity. The -1 was because we found that gamma of -1 was minus gamma of 0, which had the 1 by x. Okay. Now we have to repeat the same calculation here with this guy. Okay. Clearly, we get the same answer with u replacing t. Complete symmetry between u and t. So, from here we will get plus -1 over minus alpha prime s. So let's take that common. Minus alpha prime u minus 2. But we have the equation s is equal to 0, and therefore alpha prime t plus u is equal to -4. So this vanishes. So this is equal to
That is also alpha.
minus alpha prime t plus u plus 4. This is 0 because our pole is at s equals 0.
So it's just one. Alpha prime is divided by alpha prime is exactly.
Exactly. Exactly. We just don't have a pole at s is equal to 0. And as we said, we did not expect a pole at s equals 0. Okay? Simply because the tachyon gauge goes on, the 3 gauge goes on amplitude, vanished at s equal to, vanished at the u1 place. However, this argument was purely u1. Okay? If we look at the argument now for un, the tachyon gauge boson amplitude does not vanish. Just because the tachyon is charged at the adjoint of un. And you get the amplitude that we worked out in class, which is basically some factor of momentum times polarization difference, or momentum difference times polarization. Yeah, this is just one polarization. Momentum difference times the polarizing. Yeah, do you remember the answer after sine and a factor of 2 maybe? Was if the momentum carried by the two tachyons was k1 and k2, and the polarization of the gauge boson was k3, well, E3. Then we got E3 dot k1 minus k2 times trace of commutator of lambda 1, lambda 2, lambda 3. And we found E3 dot k12 times trace of commutator of lambda 1 to lambda 3. And then after some numbers that I'll ask you to look up in your notes, or we'll look up. Okay, so now this in the situation where we had channel pattern indices, we no longer have this vanishing tachyon gauge boson amplitude. Okay, so we should get something for the pole. So how does that work? And in order to try to see how that works, let us now go and try to correct the formula for 4 tachyon scattering to include channel pattern indices. Okay, let's briefly recall how we did it. We had K1, K4, K3, K2, and K3. Let's look at this particular order of insertions. With this particular order of insertions, we set this guy to 0, this guy to 1, and this guy to infinity. Okay? Anything involving a coordinate difference with infinity cancels out. So we just got this times this. So say the location of this guy is y. We got y to the power alpha prime k1 dot k4. Maybe it's a plus minus 1. Yeah. Was this with a minus sign? And 1 minus y, something means, okay? Minus alpha prime K, no minus. K4.K2. Okay? And then this guy, K1.K4, was the same thing as U. Right? So this guy was related to this, we wrote as K1 plus K4, the whole thing squared, minus K1 squared minus K4 squared. The other things gave us the shifts, and this one gave us the U. Okay? Whereas this guy was K1 not K2 and gave us the S. So this ordering gave us US. Right? So the ordering 1, 4, 3, 2 was associated with US. By US I mean the US community U. Okay? And let's recall now very quickly what all the other orderings gave us. We'll need this because you see all the different orderings will have different Chan pattern contributions. So we'll have to be careful. Okay. So suppose I'm just going to write out. Okay, I'm clearing all this. Okay. I'm just going to write out the 6 different orderings, and we'll try to figure out what we get for each of them. So we have 1, 4, 2, 3. This gave us US. Okay? Now, what about 1, 2, 4, 3, for instance? Okay? Just we can use the same rule. This will give us K1, K2, so that's S. This will give K2, K4, which is same as K1, K3, which is T. So this gives ST. Okay? 1, 2, 3, 4. This gives S and 2, 3, which is 1, 4, which is U. Does everyone understand how I'm getting this? Yes.
First one is UT.
Was UT?
Yeah.
First one was UT, you're probably right. This one was U, and this one was
1.
Thank you. This one is S, and this one was T. Right? This one was S, and this one was U. Correct. By the way, one check is that, of course, I'm choosing this is the first and this is the second, but you should be able to do it in any cycle. Okay? So let me choose this and this. So this one will give us T, and this will give us U. Whichever order you do it, you get the same answer. Okay, so I just choose it, one order at a time. Okay, so I've done all the 3 cyclical orderings in which 1, 2, 3 come anticlockwise. Now I'll do 1, 3, 2. So if we had 1, 3, 2, and a 4 here, then, oh yes, good. So this is U, and this is a S. Okay. Then we have 1, 3, 2, and a 4 here. This gives us a T and gives us an S. Excellent. And we have 1, 3, 2, 4. This gives us P and a U.
Yes, in the cyclic order of 1, 2, 3 doesn't matter. The position of 4 if it is in between 1 and 2, even the mirror configuration will be the same.
Position of 4 between 1 and 2. Then you're saying, sorry, give me an example. This one and whichever. of ut. You're saying 4 is exchanged with all of 2, 3. Yeah. Okay, yeah. That's probably good. Okay. So now we want to use the fact that we understand this quite well to try and include the Chan factor. The nice thing about having the answer this way is that the contributions of Chan pattern factors is obvious here. This is trace lambda 1, lambda 4, lambda 2, lambda 3. Very cyclical permutation of that. This is trace lambda 1, lambda 2, lambda 4, lambda 3. Okay? So, what two contributions give us ut? Okay? We get ut with trace of lambda 1, lambda 2, lambda 4, lambda 3 plus trace of lambda 1, lambda 3, lambda 2, lambda 4. Did I get that right? Sorry, this was 1, 4, I got it. This was 1, 4, 2, 3, right? And this was 1, 3, 2, 4. Did I get that right? One, 4, 2, 3. 1, 3, 2, 4. Looks okay. Let me check with Kuczynski. UT 1, 2, 3, 4, 1, 4, 1, 3, 2, 4. Actually, Kuczynski has a typo in old edition of 6.5.6, corrected from last time we taught this course. It's probably corrected on his website, on the new edition. It's 1, 3, 2, 4 and 1, 4, 2, 3. 1, 3, 2, 4, 1, 4, 2, 3. Perfect. Okay? So UT comes with this. So now I'm just going to write this down. I'm sorry for all the detail, but it's important to get this unitarity check right. Okay, so this comes with, I'm just going to write the orders, okay? So 1, 4, 2, 3 plus 1, 3, 2, 4. Okay. What about ST? What order does this ST come? That gives 1, 4, 3, 2. Oh God, I dropped out. Was this ST? This was S and U. Oh, sorry, what was the other ST? It's at the end.
1, 3, 1.
What was this?
1, 3, 4.
1, 3, 4, 2. Okay, this was ST. Okay, and this was UT. This is, sorry, S
TS.
and U.
Same as TS.
Yeah, TSS. Okay. So this guy, which is SU, SU was 1, 4, 3, 2, and this one 1, 2, 3, 4, and this guy, which is ST, was 1, 2, 4, 3. 1, 2, 4, 3 plus ST was also 1, 3, 4. Okay, right. Now that we have this, we can rub out these circles and proceed. So now let us recalculate. Now let us recalculate both the tachyon pole as well as the tachyon gate pole. Let's first do the tachyon pole. Okay, so we're looking at the tachyon pole. Okay, so all of this analysis stays unchanged. This and this each gives us a factor of 1. Okay, so this and this each gives us a factor of 1. It's just that the explicit factor of 4 that we had last time is replaced by the explicit sum of 4 different traces. Okay, so the tachyon pole at S equals the appropriate value comes with the factor trace of lambda 1, lambda 2, lambda 4, lambda 3 plus lambda 1, lambda 3, lambda 4, lambda 2 plus this guy lambda 1, lambda 4, lambda 3, lambda 2 plus lambda 1, lambda 2, lambda 3, lambda 4. Okay, now Kulchinsky claims this is the same as trace of lambda 1 anti-commutator lambda 2 and lambda 3 anti-commutator lambda 4. Okay, can somebody brave enough check this?
I'm getting lambda 1 anti-commutator lambda 4 and lambda 2 anti-commutator lambda 3. Is that the same? No.
Well, S channel should treat 1 and 2 as special and 3 and 4 special, right? It's S groups 1 and 2 and 3 and 4. This looks like a more accurate combination to me, but let me check. We have a lambda 1, lambda 2 here. Do we have a lambda 2, lambda 1? Yes. Lambda 2, lambda 1. First, let's get both lambda 1, lambda 2. So lambda 1, lambda 2. Yeah. So this part's working out. And this guy moving around. Lambda 2, lambda 1, lambda 3, lambda 4, lambda 4. Yeah. Kulchinsky is right. Okay. Okay. So the thing that would have been 4 is replaced by this trace. What about, by the way, the 3 tachyon scattering? The 3 tachyon scattering, the thing that would have been 2, was replaced by trace of lambda 1, lambda 2, lambda 3. And you can ask, where do you put the anti-commutator? And the answer is, it does not matter. There are 2 cyclical orderings. You sum over those 2 orderings and that can get the anti-commutator. Any 2. Okay? Now how does unitarity work? Now how does unitarity work?
Once these channel particle factors are there, our definition of CD, for example, that will also change.
The definition of CD will also change. No, you see, the CD is entirely, since boundary degrees of freedom are doing nothing. It's not contributing to the determinant at all. So CD is entirely the determinant of the bulk fields, which are unaffected by this.
The way we calculated it, like 4GQ. Now these factors are.
Let's check if that changes or not. Okay, so you see, we had a factor of 2 and that's replaced by this guy. Here we have a factor of 4 and that's replaced by this guy. Okay, so if the same relationship is to hold, and it better be the same relationship. If the same relationship is to hold, there must be an identity in channel pattern factor space. What must that identity be? The identity must be that trace of lambda 1, lambda 2, lambda 3, trace lambda 3, let's call this lambda middle. Now this we'll think of as the guy running in the middle. Okay, lambda 3, lambda 4. Sum over lambda middle, because you should sum over all polarizations of the middle guy. This had better be equal to this. This should be equal only when you correctly normalize this lambda. should be normalized so that trace lambda m a lambda m b is equal to delta a. To give it the canonical normalization for states, otherwise it is possible. Okay. Now, is this true? Of course, it's true. You see, matrices can be thought of as Hilbert space with inner product defined by trace. Okay, and in that Hilbert space, this is lambda m form a complete basis, and this is simply what we've done here is insert the decomposition of identity. Okay, so this is an obvious relationship. It's an obvious relationship, it's just true. So you see, the old relationship between determinants and 1 over G continues to work. Chant pattern factors work by themselves. Is this clear? Okay, that's very nice. But it's not so, I mean, it's okay. But it'll be even nicer now when the gate goes on. Because previously we got something that was 0. Now we get something that's non-zero. Okay, so let's see how that goes. Okay, everyone clear with this? Okay, fine. Now, how does it work with the gate? We already saw that this diagram gave a factor of minus alpha prime t minus 2. And we got the same times some pole, some overall sign which we're not caring about, times the pole s. Okay? And then we got the same factor from that guy, but with the minus sign. So now we get this answer. But with trace of lambda 1, lambda 2, lambda 4, lambda 3 plus trace of lambda 1, lambda 3, lambda 4, lambda 2 minus trace of, now we want this guy, right? Lambda 1, lambda 4, lambda 3, lambda 2 minus trace of lambda 1, lambda 2, lambda 3, lambda 4. Now what do you think Polchinski claims in this case?
It's commutator 1 to commutator.
Exactly. But this, according to Polchinski, is trace of lambda 1 commutator lambda 2, lambda 3 commutator lambda 4. Let's check whether that's true. Lambda 1, lambda 2, lambda 1, lambda 2, 4, 3, 3, 4, up to maybe a minus. Yes, probably minus. Okay, and what about lambda 2, lambda 1? Yeah, 3, 4, and lambda 2, lambda 1. Yeah, works with a minus. Okay? So that's great. Why is this the good index structure from Chant pattern factors? Do you see that this is exactly what we needed from unit M? Because recall the tachyon gate boson had the commutator. Why did it have the commutator, by the way, in field theory? Because the tachyon is in the adjoint representation. That's where the commutator comes from. Okay? Then the scattering of tachyon gate boson was proportional to lambda 1, lambda 2, lambda middle. The lambda middle is the polarization of the what? Gate boson. Okay? But now precisely the previous analysis goes through. If you take this times trace of lambda middle, lambda 3, lambda 4. Sum over all lambda middles. That's the same as this. From the same argument. So you see the Chant pattern factors, the indices are working out by themselves. Okay? So we can let the tan pattern factors be and look at the momentum dependence. That's what remains in order to take care of that. Okay? Now it's a little less trivial than before because we got this minus alpha prime t minus 2. It's not just a constant. That has to work out. Okay? Let's see how that goes. Let us recall. Okay, I'm clearing this part. Everyone fine? Okay. Let us recall how or what the amplitude the tachyon gave us an amplitude was. After a factor of 2, which I pull out from Bulchinski or from your notes at the right point, we had K1 minus K2 dot polarization, just one polarization in the game is one photon. Okay. K1 minus K2 dot polarization. Okay? So, now when we've got 1, 2, going to some middle things, and 3, 4. Okay? What are we going to get? We're going to get K1 minus K2 dot E into E times K3 minus K4. What do we do with the polarization vector? Sum it over everything. Okay. So once again, this is like insertion of identity in the middle. So K1 minus K2 dot K3 minus K4. Okay? So let's work that out. So K1 dot K3 plus K2 dot K4. Okay, K2 dot K4 minus K1 dot K4 minus K2 dot K3. Now remember we have 4 tachyons. All of them are tachyons. All of them obey K squared is equal to, it's always tricky, right? It's minus alpha, it's plus alpha. Alpha prime K squared is equal to 1. Right? Because alpha prime is mostly spatial. So if it's a positive number, it means the mass square is negative. Okay. So all of them are obeying alpha prime K squared is equal to 1. Okay. So what we do is we process all of these as this is K1 plus K3, the whole thing squared, minus K1 squared, minus K3 squared, divided by 2. Okay. And this object here is just T. Let me just put in the right alpha primes. All of them, they would have been alpha prime. What? Well, I just have an alpha prime here. And then into the end. There's overall alpha. So this object is what? This is alpha prime T minus 2. That is good. Or was this minus alpha prime T? So that of course. Because K1 plus K2 squared is minus. Minus alpha, that's looking better, right? What was our, I rubbed it out. What was our pole? It was minus alpha prime T minus 2, right? Alright. It was alpha prime T minus 2. Okay. This divided by 2. What about this guy? It's the same because K2 plus K4 is same as K1 plus K2. So it's the same. We can remove the factor of 2.
Actually, all the K1 squares, K2 squares cancel.
Squares. But let's not think of it that way. We just, each of these is whatever it is. K1 square is minus 2. Okay, what about here? Do you say that we will get minus alpha prime u minus 2, but with a minus sign? And remember, we've already seen that minus alpha prime 2 minus u is minus of minus alpha prime t minus u. So all of these factors combine to give us a factor of 2 times minus alpha prime t minus 2. The minus sign has been accounted for. Okay? So, the t dependence is right, it's absolutely perfect. Okay? The t dependence is right, just perfect. Okay? All we have to now do is to account for the right factors of 2. But factors of 2 are no problem, because we do not yet know what the relative normalization between the coefficient of the gate-boson vertex operator and the coefficient of the tachyon vertex operator is. We know that they're both proportional to the open string coupling, but we don't know what the relative normalization is. So the factors of 2 we will use to determine that relative normalization. See, it's very important that you didn't get a factor of t. You can't absorb a factor of t into a relative normalization, because t is not a property of what one guy is doing. It's a property of what one guy is doing and whom it's meeting. Okay? The normalization is about your vertex operator, not what's going to happen to it. Okay? So the STU has to work out. The remaining part can be absorbed into normalization. Now, it would take one further iteration with one further level of care to get the normalization right. Let's trust Polchinski on this one. You guys can work it out. Okay? What's the structure? Let's understand the structure. Here we look at CD squared times GT squared. GT to the 4 times G gate boson. I can't remember what we called it last time. Let's call it GG squared. Is equal to CD times GT to the 4 times some number. Okay? So now this GT to the 4 will just cancel, and we will get CD. Okay, let's use this to write this as CD. Let's use this to solve it. GG squared is equal to 1 by CD times some number. Okay? But 1 by CD we already knew was 1 over G tachyon square. So up to a number, what we're going to get is G gate boson square is number times G tachyon square. Okay? Now, Polchinski tells us that number is, that what he actually finds is GT squared, so 1 over 2 alpha prime. Sorry, G gate boson squared, 1 over 2 alpha prime. This is what comes. Now, 2 exercises. First, keep track of the numbers in the diagonals. Second, check that the same relative normalization comes out of the state operator. Okay? The operators that we have to insert into the path integral are not arbitrary. They are the operators that correspond to a state with unit norm. So the number behind the operator, if we want to get not just a state proportional to the one we were interested in, but the guy with unit norm, the number behind the operator is fixed. Okay? And check that the vertex operator, check that e to the pi k dot x corresponds to the unit norm, corresponds to 0k. This is actually correct. Yes. Then e to the power I k dot x del mu x del mu x divided by 2 alpha prime. Okay, let's do it. Okay, fine. Corresponds to the state d mu alpha minus 1 mu. Okay, and assuming that this guy is unit normalized, this is a normalized state provided for this reason. Okay? All of you know how you're going to check this, right? You're going to check it using all the same path and tensor manipulations that we used before. Okay? I'll leave it as an exercise for you to check this. Okay? In particular, one way to check this would be to show that if this was the case, then alpha 1 acting on this state should give you exactly the state. So, suppose I do it less fancy, I do it in the one boson theory. Just 1x, no epsilons. Okay, so del x by x. Okay? So check the normalization of that. So the baby version of this problem is to check that dx by 2 alpha prime pi k dot x corresponds to the state alpha minus 1 from 0. This is the baby version of the problem. Okay, how would we check this? One way would be, see, if this was true, then alpha 1 acting on the state would give us the state 0k. So if this was true, then alpha 1 acting on the state would give us the state corresponding to the insertion of e to the pi k dot x. Right? But alpha 1 we know how to write. Alpha 1 is a contour. So how do we get alpha 1 acting on this state? We insert this operator and then surround it by a contour with a precise normalization, which we know. The contour for alpha. Then shrink the contour. Okay, you get the OP. That OP will give you the e to the pi k dot x with a particular coefficient. And with this normalization, that coefficient will be 1. Is this clear? This is an exercise you guys can do. Okay? Is the logic behind it clear? Excellent. This, by the way, I've only worked it out for a couple of levels, but it always works out. Okay? We will go through at some point proof of unitarity, certainly at trade level. The proof of unitarity at loop level, this is sort of proof of unitarity at loop level. But that sort of proof of unitarity ignores various subtleties. Okay, it's the kind of thing that Ashok is really trying to clean up now. Okay, so we want, I'll give you the idea behind the proof at loop level. Problem with these, there are formal proofs which can be invalidated by infrared divergences. Divergences of various sorts. Okay, we won't get it. But then, at some point in this course, I'll give you a clean proof at trailer. Okay? And formal and half of a proof of unitarity of string theory. What's the basic idea behind the proof? The basic idea behind the proof is that there is this key relationship between spacetime and the worldsheet. On the worldsheet, we have an operator product expansion. You have two operators coming close together, two operators coming close together here. We exchange things. It's this term in the operator product expansion which leads to the corresponding state being exchanged in spacetime. Okay? And then the unitarity of the worldsheet conformal field theory just directly imprints itself into unitarity of spacetime. That's the basic idea. And then there are hoops you have to go around to make that idea precise. Okay? This always works. And so we'll... Okay. I propose we stop our first round discussion of open string Lyapunov scattering here for questions and comments and move on to the closed string. We'll come back to the open string right at the end of this lecture to look at high energy scattering. But I propose for now we move on to closed strings unless there are questions. Questions, comments, discussion of any sort.
So I can understand why is it necessary that word shape unit directly should be translated as space variable?
Wait till the lecture on that. Why is it necessary? I'll give you a lecture. Perhaps it's not too unintuitive that it will work. You know, the basic idea is what is it? See, the basic idea is it's the same structure of variables. In an OPE, you've got this structure where the 4-point function is determined by 3-point functions squared with some exchange. Same thing's happening in space. So the fact that the 4-point function here is 3-point function squared essentially gives you unitarity in space time as well. Okay, but hang on if you want more detail. Hang on. Any other questions or comments?
We'll always have, like, for higher and higher and higher cores, more and more and more massive states being interchanged, but no loops appear.
This formula was a true trade-off. Because we did the calculation of the disk. Remember that if you want, let's say, open string loops, you would have to do a calculation of the randomness. Okay? Because you see, this diagram in the point particle limit will become, whereas this you should just think of as being shrunk. So the point particle limit is just tree level. So far we've only done a calculation at tree level. We did classical string. So you will never get any singularity more dramatic than a pole. And of course, it's how it should be. When you do loops, more you'll get branch-outs. Okay? Any other questions about that? Okay, let's move on to the clustering. So, when we were studying so we can finally rub off the top formula. By the way, there's one thing I should say. Notice that spin 1 exchange gave a function linear integer. And we sort of understood why. Let's understand why in a little more detail. You see, I told you that by direct computation we found that k1 minus k2 dot e was the structure that appeared when we did the 2 tachyon to 1 gate goes on computation. But let us see whether this was a coincidence of the specific couplings of strings carried or this follows from Lorentz integrals. Okay? So let's see. Firstly, we know, what do we know about E? We know that K3 dot E is 0 because the polarization is transversed to the momentum. Therefore, from momentum conservation, K1 plus K2 dot E is equal to 0. We already know that any dot product built up as just the 3 momenta is just a number because it can be expressed in terms of the mass system, the 3 on-shell particles.
How did your particle number become the Hamilton direction?
Sorry, how did what?
K3 dot E is 0 because E polarization the transverse.
Transverse, yes.
Then see the particle number.
Yeah, we're looking at the scattering of 1, which is the tachyon, 2, which is the tachyon, to 3, which is the photon. Yeah, so 3 happens to be the special guy because it's the photon. Okay? So we know that K1 plus K2 dot E is 0. K3 dot E is 0. What is the leave? It leaves only k1 minus k2 dot e. That's the only Lorentz invariant left in the problem. Okay. Moreover, the amplitude has to be linear in the polarization vector, because the polarization vector is an external state. Okay, so you can't have this thing squared. So the only possibility from Lorentz invariance was k1 plus k1 dot plus k2 dot e. There's nothing else you can write out that is not just that's your number. Sorry, k1 minus k2 dot e. Okay, so though we got the answer from string theory, the momentum dependence was not a feature of string theory, it was a feature of Lorentz. Okay, so this, now you remember we deduced that the pole in S had to be minus alpha prime t minus 2 just by squaring the circle. Alright? That again therefore is not a feature of string theory. It's a feature of Lorentz invariance. So we had determined that in any for particle scattering, for a scalar scattering, in any for scalar scattering, where the exchange particle is spin 1, gate goes on. Okay? In any such thing, the pole dependence is a linear function of t. Let's actually generalizes this. Okay? In scalar to spin S scattering, the pole dependence is always a polynomial of t whose degree is S. The residue of the pole is always a polynomial of t whose degree is S. Let's actually quickly check that this is working out in our NCS. So sorry, go ahead. Gamma minus S minus alpha prime S minus 1 gamma minus alpha prime T minus 1 gamma alpha prime U. Is this blue irritated? Is blue visible? Yeah. Let us look. You see, as you remember, when you go to higher and higher levels in mass, you access higher and higher spins. You have the possibility of accessing higher and higher spins simply because going to higher levels is adding more derivatives. More derivatives. For instance, at one higher level you could have del x mu times e to pi k dot. You could have this kind of vertex operator. Okay? So you get two indices. At one higher level you could have another del x rho. So you could have three indices. So you have at level. So let's say that the level is the number of units of dimension above the vacuum. Okay. So at level n, you have particles of spin up to n. It's only up to because there's another way of getting it. We could have del square x, or we could have del x with indices contracted and so on. We'll have to play the game carefully. Okay? But it's clear you cannot get more than spin S at level S.
We don't have masses character.
What? Well, this is because we're getting the open string. From the closed string, we would get this stuff times an anti-holomorphic sector. So we let del x mu, del by x mu. Okay, so we do have masses. But at the moment we're looking at the open string. Where there are no masses, right? There's masses photon. Right. So So you see that at level n, you cannot have spins greater than n. What I want to show you is that the residue of the pole corresponding to a level n exchange is a polynomial of t whose degree is no larger than n. Okay? So what's the mass square at level n? At level n, S, alpha prime S is equal to n minus 1. Because at level, at level 1, it should be 0, so that's right. And level 0 is minus 1, so that's right. Yes? Okay? So suppose I substitute alpha prime S is equal to n minus 1. I want to check that what I get, that the residue of the pole, is a polynomial in T whose degree is no larger than n. Okay, so this terms will give me my pole. The ratio of these two will give me my residue. So what do we have? We have gamma of minus alpha prime T minus 1 divided by gamma of minus alpha prime, plus alpha prime U plus 2. Now remember that alpha prime into S plus T plus U is equal to minus 4. Okay, so first substitute in alpha prime S is equal to n minus 1. So we get alpha prime U is equal to minus 4. Let's say alpha prime U plus 2 is equal to minus 2 minus of alpha prime S n minus 1. Okay, which is equal to minus 1 plus n minus 1. Okay, and I follow the T minus alpha prime T minus alpha prime T. So this ratio becomes gamma of minus alpha prime T minus 1 over gamma of minus alpha prime T minus 1 plus n. Now it should be clear that we get a polynomial of degree. This degree is not higher than minus n. Okay? Because we use the same formula. This is minus alpha prime T minus 1, minus 2 into minus alpha prime T minus 3 until we reach minus alpha prime T minus n plus 1. How many such terms are there? Yeah? 2, 3, up to n plus 1. So n such terms. So this is up to an overall number that comes from the strength of the pole, which you have to calculate. Yeah? This is the residue of the pole of exchange. This is the residue of the pole, and that residue is clearly a polynomial of degree n.
So if you want something of degree less than n,
yes,
then actually first two terms have to cancel between each other and the third term might.
In fact, the way it works is that without Chern-Patten factors, every order level is just gives 0. Okay? And every even level, there's no cancellation. They just add up. Okay? With Chern-Patten factors, there's just never any cancellation. You just get different Chern-Patten structures. So that kind of cancellation you're talking about doesn't happen. And the reason is that spin S exchange actually does contribute a polynomial not of less than S, but a degree equal to S. And it's just a fact of string theory that tachyon spin S for open strings is 0 for S is odd, but non-zero for S even. So for every even S. Okay? But when you add the Chern-Patten factors, it's 0 for nothing. By the way, there's an interesting kinematical exercise here, which I'm sure somebody's done, but I don't know the answer to. It's interesting to know what, like we argued, like we've explained, the T dependence. You see, you can ask, if you take any scattering amplitude corresponding to four scalars with the exchange of a spin-S particle, you could ask, well, what can we say about the residue of that pole? And what I've tried to explain to you, although I haven't given you the details, is that the function of T that comes behind, that comes as the residue of the pole, is entirely determined by Lorentz frequency. So, if you have a spectrum of particles that can be exchanged, you can parameterize classical scattering. Yes, please. Scalar scattering just by some bunch of numbers. The numbers that can appear behind fixed structures times things that have no non-analyticity. Okay? Which expanded in different ways gives us all poles. Okay, this is called channel duality. This is one of the beautiful results. Okay, sorry, but what I was saying was that we've seen that this scalar scattering is completely determined. Actually, I don't really know the answer to this question. This just my ignorance. Somebody knows this. Maybe. But about how that works with graviton-graviton scattering. Suppose you take graviton spin S, just two graviton. To what extent does Lorentz invariance determine this 4 point, the structure of this 4 point symmetry? Presumably very tightly. And it would be easy to work out, but I don't know the answer to this. Sort of interesting in the context of recent discussions about causality and so on. Okay. So let's move on. Let's move on to studying closure. Okay, so in order to determine the four taxion closed string scattering amplitude, okay, things are very similar to what we had in the three tachyons. So, as before, let us suppose that the fixed vertex operators are at 0, 1, infinity, and the unfixed, these carry momentum k1, k2, k3. The unfixed vertex operator is at something. Okay, so first we need to get rid of the costs, and then we need the e to the pi k dot x insertion. Okay, so the costs are very easy. We will Z12, Z13, Z23, 1 square. Okay, as before, Z12 mod square is 1 because we fixed this. Z13 and Z23 are infinity mod square. These infinities are better cancelled with infinities that we get from the matter of insertions. Okay? Now, let's remind ourselves about our formula for the mathematical insertions. We are equal to pi k dot x, k1 dot x of z1, equal to pi k2 dot x, z2, pi k3 dot x, z3, equal to pi k4 dot x of z4. Now, in an earlier lecture, we worked out that this was product over ij, zij, to alpha prime will be 2 ki dot kj. Can someone go back far enough in the notes to check this factor? I'll try to put it here. No two. Ah, beautiful. I found it. Yes, exactly. Okay. So now we need just to apply this formula to this case. Now, as before, if things are working out right, anything involving Z3 should just vanish. I mean, should cancel against this infinity square. But otherwise, just vanish. Now, once we have Z3, whether you have Z1, Z2, or Z4 doesn't matter because Z3 is infinity and infinity minus anything finite is infinity. Okay. So we have infinity mod square to the power k3 dot k1 plus k2 plus k4 according to this formula. That's the dependence of Z3 in the formula. But that is infinity mod square times k3 dot minus k3 by momentum with an alpha prime. But now our mass shell condition is that for the closed string. Right? Our mass shell condition is that for the closed string, and if I remember rightly, minus k3 squared is equal to minus 4.
Why is it infinity square? Like it should be just infinity.
Ah, this should be it. Thank you. Excellent. So, this is infinity mod infinity to the power minus 4. But here we have mod infinity to the power plus. So those cancel. Okay? So the Z3 insertions, the fact that we take Z3 to infinity simplifies the formula but doesn't make it nonsensical. So now we can just throw away every Z3 dependence from here and proceed. Done. Okay? So what's our final formula? Our final formula is integral into Z, so we have to integrate over the unfixed vertex of mod Z to the power alpha prime k 1 dot k 4 mod Z minus 1 mod to the power alpha prime k 2 dot k 4. So that's it. It's a pretty simple formula. Okay. However, this simple formula appears to have broken the democracy between ST and U. It's very strange because we started with a completely democratic formula, and it looks like it's broken the democracy between ST and U because this guy looks like it involves U and this guy looks like it involves T. But that doesn't seem like something involving S. Of course, that democracy breaking is fake. It comes from the fact that we did some fixing. And you can do changes of variables to show that you go to similar expressions in terms of S and T or U and T. Okay? But perhaps the easiest way of showing that we've got a democratic formula is just by evaluating this integral. Okay? Now this integral is a famous integral in complex analysis. I'm going to give you the answer and leave the derivation of the formula as an exercise to you. It's worked out in great detail in the textbook of Green Schwartz and Wheaton. If you're interested in actually, I'll give you a hint about how to go about it. The formula that e to the power minus t times mod z squared times t to the power n. Okay. dt. So, the formula that this object here is equal to gamma of n times this is t to the power n, so times homogeneity I suppose z mod z to the power 2n. Okay, the right version of this formula is a useful thing to use. When you've got these mod z's, as you do in this thing, it's useful to put them up in the exponent by introducing the Lagrange multiplier. Anyway, so there are some hints in exercise 6.10 of Buczynski's book, and it's complete workout and screenshots and written. I leave it to you to derive the formula. It's just an integral formula. It's a nice integral formula. It's a beautiful formula. So the formula I'm going to ask you to derive is the following formula of complex analysis. D2z, yeah, D2z mod z to the power 2a minus 2. 1 minus z to the power 2b minus is equal to 2 pi into gamma a, gamma b, gamma c over gamma a plus b, gamma a plus c, gamma b plus c, where c is defined so that a plus b plus c is 1.
Yeah. So c to the 2n plus 2 or something like that down there.
Yes. That's the major factor. Yeah, probably plus 2. Yes. Right. Thank you. Yes. Okay. So this is the formula I'm going to leave as an exercise for you to derive. We're going to use this formula. Okay. In the processing of this object. So in order to use this formula, it's nice to firstly express this in terms of SDNU. Okay, so let's do that. Okay, so let's do that. So alpha prime k1 dot k4 is equal to alpha prime k1 plus k4 squared minus k1 squared k4 squared by 2 is equal to minus u okay, now what? Minus alpha prime. Minus alpha prime u plus 2, and now this is minus 1/4. Yeah, minus 1/4. Sorry, minus 4. So minus 8. Minus 8. Eight sounds like straight, slightly straight. Okay, maybe it's correct. Let's move on to the correct. So we have, we write this as yes. Maybe it works out. Okay, let's see. So this is d2z mod z to the power minus alpha prime u by 2 minus 4. 1 minus mod z to the power minus alpha prime t by 2 minus 4. Okay? So if we're going to use this formula, we need first to find C. So firstly we find A and B. So what's A? So A, so we're supposed to take away 2. So A is equal to minus alpha prime u by 2 minus 2. B is equal to minus alpha prime t by 2 minus 2. So C, let's check if C is equal to minus alpha prime s by u minus 2 works. Let's check. In order to check that, we have to check whether A plus B Ah, 2A. Thank you. 2A. 2A is this, 2B is this. So let's check if 2C is this works. So, just
that gives A plus C plus C equals 0.
that gives 0? No. Yeah, let's just check what it gives. It gives 2 into A plus B plus, I think it works. 2 into A plus B plus C is equal to minus alpha prime u minus alpha prime t minus alpha prime s by 2 s plus t plus u by 2 minus 6 right, minus 6. Now alpha prime into s plus t plus u is minus 4. So minus alpha prime into s plus t plus u is plus 4. Plus 4 by 2, so that's sorry. Almost, sorry, just
S plus T plus U is 4m squared is minus 4m.
Thank you. So S plus T plus U is equal to 4m squared, and m squared was minus 6. So alpha prime is equal to minus 16. Thank you. Okay. So
8 minus 6, which is 2.
wonderful. So we get 8 minus 6. 2 into A plus B plus C is equal to 8 minus 6. Therefore, A plus B plus C is equal to 1, which is what we want. Okay, so we see that this identification of A, B, and C works. So let's recall, let's put identification back on the board. Identification is A is equal to minus alpha prime U by 4 minus 1. B is equal to minus alpha prime T by 4 minus 1. C is equal to minus alpha prime C is equal to minus alpha prime S by 4 minus 1. And with this identification, this is the formula. Let's write out the formula. The formula is 2 pi into gamma of minus alpha prime S by 4 minus 1 minus alpha prime T by 4 minus 1 gamma of minus alpha prime U by 4. translating into gamma of minus alpha prime S. Now maybe we can simplify A plus B because it's 1 minus C. So that's 2. So 2 plus alpha prime S by 4 gamma of 2 plus alpha prime T by 4 gamma of 2 plus alpha prime U. Okay. Now, remember the closed string mass shell formula. The closed string mass shell formula was the mere of 4 divided by alpha prime m squared was equal to 4 divided by alpha prime times oscillator number times so. The closed string mass squares were spaced in units of 4 by alpha. That fact is reflected in the fact that the argument of our thing is alpha prime S by 4. So that the spacing of poles will be precisely at the location of the closed string, at the location of closed string sets. Okay? Now, this formula, you see, it's just one formula. It's not the sum of 3 numbers. It's just one formula, and it in itself contains poles or all poles in the S channel, U channel, and T channel, all in this one formula. Okay, let's we'll stop at 5 minutes. Let's quickly just try to analyze the tachyon pole in the S channel. It's very similar to the open string. Let's quickly analyze the tachyon pole. So the tachyon pole is at the argument of this gamma function being approximately 0. So it's 1 over the tachyon, S of the tachyon mass times whatever this stuff evaluates to at alpha prime S is equal to minus 4. And times alpha prime S by 4 is equal to okay. So let's see. So firstly, what do we get? We get gamma of minus alpha prime. Okay, let's play the same game. We'll eliminate U. Okay, because alpha prime into S plus D plus U is equal to minus 16. But we have alpha prime S is equal to minus 4. And so we get alpha prime into T plus U equal to minus 12. Okay. Therefore, alpha prime U by 4 is equal to minus 3 plus minus alpha prime T by 4. Okay? So now let's write out, apart from the guy that's giving us the pole, which is this guy, let's write out what all the others are. This chap is simply gamma of 1, which is 1. Right? So we get 2 pi, we have gamma of 1. Then that chap was gamma of minus alpha prime T by 4 minus 1. That chap was gamma of minus alpha prime U by 4 minus 1. Minus alpha prime U by 4 is plus of all this. Minus 1 will make this a 2.
So 2 plus alpha prime.
Yeah, 2 plus alpha prime U by, sorry, T by 4. Well,
That
cancels the denominator, exactly. So this is gamma of 2 plus alpha prime T by 4, and this guy is simply gamma of So these two chaps cancel each other as they have to from unitarity. Okay? Now, we'll do one more of these exercises. This one more exercise is sort of interesting exercise. It's the contribution of the the exchange. The contribution of the exchange purely from the massless state. Massless state is the graviton. Okay?
There will be another factor because the gamma minus alpha prime x by 4.
Oh, sorry, say again?
Basically, if we consider the pole in S, then
There might be
You're saying there's a factor of 4.
Yeah.
That's a normalization. Yeah. Yeah. This is the pole of alpha prime s by 4 minus 1. Yeah. We have to get those numbers right. Sorry, what?
I was thinking that since it's a ratio of two gammas, both in S, there might be some values of S for which both the numerator and denominator arguments become negative.
Both the numerator and the denominator arguments become negative. Okay, let's take a few examples. Let's just look for, where. You see, when this guy is negative, this guy is not going to be negative. Yeah. Okay. You'll see that. We'll see in a few minutes. Okay. Now let's take S is equal to 0. S is equal to 0. Therefore, we have alpha prime t plus u is equal to minus 60. So alpha prime t by 4 plus alpha prime u by 4 is equal to 4. Okay? So, S is equal to 0. This gives us a gamma of 2, which is one factorial, which remains 1. This guy gives us the pole. So we've got some 2 pi and not be very careful about the factors, so ignore 2 pi. It's these guys that are of interest. This. Okay? So, once again, let's eliminate, let's say u. So we get gamma of minus alpha prime t by 4 is 1. Gamma of, now, minus alpha prime u by 4 is plus alpha prime t by 4 plus 3. Exactly. And that's divided by gamma of alpha prime t by 4 plus 2 into gamma of, now we want to take, this guy is minus 4 plus 2, so minus 2 and minus. Okay? So, now let's look at this divided by this using the formula for gamma function. This is gamma t by 4 plus 2 in the numerator times the gamma that cancels this. And this guy is minus alpha prime t by 4 minus 2 times the gamma that cancels this. And so what we get is alpha prime t by 4 plus 2 the whole thing square. Up to some sign. Those are gains. Okay? So, we got this nice formula which at slightly high energies is p square. Okay? This is exactly right for graviton exchange. This is exactly right for graviton exchange. In fact, that is the same thing that comes out of the 3-point tachyon graviton vertex operator is easily seen. You see, our tachyon had momentum k1, k2, and then our graviton is going to hit K3 with an even polarization. Okay? And the effective calculation was one on the left moving sector, there was one on the right moving sector. Each of those calculations was just like the photon. Okay? So basically what you get is K1 minus K3 mu, K1 minus K2 mu mu. Okay, that is the 3-point function of tachyon with graviton. Okay. And therefore, when we take the 4-point, we have to take this 3-point carry square, sum over all polarizations. So sum over all polarizations is just identity in both mu and mu space. Every polarization. So it's K1 minus K2 all things square times K1 minus K2 all things square. And this is exactly the kind of factor that we evaluated for the open strings. The only difference being that when we express in terms of T, there is extra funny force because of the mass shell conditions being different. Okay, so it's exactly the analog of that minus alpha prime T minus 2 is just this factor, it's minus alpha prime T by 4 minus 2. And then that whole thing first. Which is exactly what it is. Okay, so the residue for tachyon going through graviton to tachyon is exactly what you should expect from unitarity. So once again we can use the same process to determine the determinant on the sphere in terms of the closed string tachyon, the number that comes behind the closed string tachyon vertex. And then once again we can use the same process to determine the number that comes behind the graviton vertex in terms of the number that comes behind the tachyon vertex. So in the end, okay, so far independent in the closed string and open string sector, but they won't remain independent long.
Why does it not have the contribution by the exchange of spin 1 mass?
Because we've got only closed strings. There are no spin. You see, our vertex operators are d mu x, d mu bar. So either you have two mu's, either they contracted so you get spin 0, or they were both there.
And this argument of unitarity is because of Katkowski, that we are cutting it into two parts.
Exactly. The argument of unitarity is Katkowski's rules, which tell you that the imaginary part of any amplitude is entirely determined by it's basically the S dagger is equal to 1. Okay, so the S, which is S1 plus IT, 1 plus IT times 1 minus IT dagger is equal to 1. That gives you I of T minus T dagger is equal to TT dagger. Then insert a complete set of states between TT dagger. So that tells you that the imaginary part of T is related to TT dagger. Yeah, that's good question. Exactly. So, yeah. So, once again, we can play the same game and determine the sphere partition function in terms of the number that comes behind the graviton vertex operator. Sorry, the tachyon vertex operator. Then determine the number that comes behind the graviton vertex operator in terms of the number that comes behind the tachyon vertex operator. When you do that, I'll just give you the answer for that. You get G graviton is equal to 2 by alpha prime G tachyon. It's the usual thing that the closed string is behaving like two copies of the open string up to some factors of 2 that float around the place. Okay, so last time we had a square root. The square root has gone away because there's like 2 copies of the open string. Last time, if it had just been the square root, 1 over 2 alpha prime. There's 2 by alpha prime. It's the same 2 that comes in change Marshall condition. It's a very irritating 2. Apart from the 2's, it's basically the same thing. Okay? Great. I think we'll stop today's lecture here. We'll discuss more implications of these formulas. We'll talk about high energy scattering and a little more about channel duality of this Virasoro. This is called Virasoro-Shapiro amplitude. Okay? We'll talk about channel duality and high energy behavior of the Veneziano. The first formula I should have said is called Veneziano formula. Second formula is called Virasoro-Shapiro formula. Veneziano formula was birth of string theory. Okay. Just 1 minute about this. I guess you know it, but anyway, let me say. How string theory was born. You know what people were doing? People were trying to study strong interactions. And when they were studying strong interactions, they found a complicated mess of stuff. Because you've got mesons of higher and higher spins. Okay? At that time, they didn't know at all what was going on. That each meson was sort of an elementary particle, or maybe not. They didn't really know what was going on. There was a zoo of mesons, and they wanted to put some structure to it. Okay? And they wanted to understand meson scattering. It was also the days of S-matrix theory. The days guided by Landau's philosophy, which Landau had famously said that quantum field theory is dead and should be buried, but with appropriate honors. It's very nice. It's totally wrong, of course, but because anyway. So it was the days in which you were trying to understand physics by consistency without using physics, which it was no Lagrangians, no dynamic principles, just use consistency, unitarity, analyticity, things like that to try to get everything. Which, from today's point of view, sounds both very prescient as well as very strange. You throw out so much by doing it, but it's not like it's never worked. It works in 2 dimensions, for instance. His advisor worked in 2 dimensions. Partly. Anyway, polyglot. Okay. So it's an idea that's not complete nonsense, but, it's too narrow. But anyway, so these were the days. And Veneziano in those days wrote down a formula. So one of the challenges in those days is very similar to something that people are now talking about, which was trying to find a formula for scattering that obeys many nice consistency properties. And Veneziano wrote down this formula, and then Virasoro-Shapiro generalized it to get a formula which was manifestly unitary, sum over poles, the right positivity properties, and had this magical property of channel duality. That is the same formula gave you S channel poles, U channel poles, T channel poles. It was clear that it was a very beautiful formula. And it was obtained in the process of trying to understand strong interactions. Then people put a string theory interpretation to this. The formula came before the theory. People put a string theory interpretation to this. You realize that these Regge trajectories come out of quantizing string, and the machinery of string theory began to be built up. And then was it 1974 or so, when 2 people, I think Yonea and Schwartz and collaborators independently realized that you get a massless spin 2 particle in this model. It took a long time for them to realize this. And so they said, oh my, doesn't look like this is a good theory of strong interactions. Which was sort of good because asymptotic freedom had happened and a good theory of strong interactions had been found. But maybe it's a good theory of gravity. But the cycle really turned, at least the first wheel, only in 1997. You see, there's something very strange about trying to find a theory of the strong interactions and hitting upon a theory of gravity. Why did that happen? We realize now, because things like the ABS-CFT duality mean that it's not an either-or question. You can be doing both. You could be looking at a theory of strong interactions and a theory of gravity. And that's what those guys realized in the 1960s and 70s in a baby way without understanding. By searching for theory of strong interactions, they hit upon the theory of gravity. We now sort of understand better why that happened. So it was in the 1990s, if you were given a field theory string theory class, you would say, it's such a strange coincidence that you find the theory of gravity relevant to the theory of strong interactions. Nobody would say that now anymore. It's not a coincidence, because duality. Yeah, so it's a beautiful history that's come a full circle and keeps going. This formula is a beautiful part of the subject. It's a very important part. It's what started the subject and not yet been completed. For instance, Veneziano wrote down his formula by requiring certain properties of it. He found an example that satisfied those properties. Okay, only poles, channel duality, unitarity, meaning positivity of coefficients. Maldacena asked Veneziano a couple of years ago in the context of this causality thing, has anyone tried to show that your formula is a unique formula that satisfies your properties? This is not to my knowledge. Just this, about stuff that was done 40 years ago, there's still new and interesting stuff to do. And we're coming back to that. Anyway.